today. So I'm talking about deep learning for the smart grid. So I was quite keen to get that increased bit of the conference, so I thought if I could pack in as many buzzwords as I could into one sentence, it's probably a good start. I couldn't quite get in blockchain, unfortunately, so sorry about that. This is a piece of work I did for a client this year, looking at electric vehicles. And I'm a consultant. I work for TCP in Cambridge. We develop products, software, hardware. This is, for us, I guess a bit unusual because it's a software project. Normally we do combination of software, hardware, optics, cameras. But this is pure deep learning. Change the slide on this. Seconds to give a short presentation. Okay, I'll do it by hand. So I thought I'd start off with two graphs, just to illustrate the case in point. So this is new registrations per year of electric vehicles. In terms of growth, the cumulative number is almost exponential. This has been aided by government grants, tax incentives, etc. And I think we all know that in the next 20, 30 years, the market for automotive is going to shift dramatically away from petrol and diesel into hybrids and all electrics. So the demand is growing massively. And if you look at the power consumption, so on the left we have the power drawn by the three kinds of domestic chargers you're seeing at the moment. So the slow, the fast, and the rapid, so that's a three-phase charger. And the y-axis here is power consumption in kilowatts. On the right-hand side, you see the typical domestic usage. So over 24 hours, you might average between half to 1 kilowatts. When you come home from work, maybe 6, 7 p.m. in the evening, you turn on the TV, the lights are on, the oven's on, you might see a spike up to 8 kilowatts. But from that you should see that the power drawn by electric vehicle charging is equal, if not greater than, the current average domestic use. So these vehicles are facing quite a big load onto our power grid. So here's what I'm going to talk about. I'm going to quickly introduce power distribution networks and the electrification project, so what it is and why we did it. Talk a bit about the work that I did on modelling demand growth using deep learning. So this is a signal processing exercise. Can we look for signals in noise, essentially? And talk about how we captured data, how we prepared it, how we chose and trained models, and a bit about deployment, although not much here. In the conference there have been a few talks on deployment, which are probably wanting to the mind, so I'll leave that to the experts. And I'll wrap up with some talk about the future of the smart grid. So what it is, what's going on, and what are the technologies. Okay, so here's like an overview of the power distribution network. On the left you've got generation, on the right is the consumer. And this bit at the end, this distribution substation to the consumer, is what we call a low voltage feeder. So there's about 1 million of these lines, and they go from a substation to maybe a street or your houses. You might have 50 to 100 houses on that feeder. Now we are seeing a change in the way that we produce and distribute energy. So rather than being like a process from the power station down a line to the consumer, we're starting to see certainly a diverse range of sources, things like renewables, hydro, particular wind. We're starting to see local generations. People are having their own turbines, they're generating their own electricity, with solar as well. We've got power storage coming online. So in the past, if we wanted to store energy, we might pump water up a hill and keep it in a dam. Now we can store it in batteries quite efficiently. And finally, the load pattern is changing. So Okay, so we've had things like electric showers, ovens, which use a lot of current, but also electric vehicles are high load for a sustained period of time. So the supply and the demand is changing. This is the power draw on a typical low voltage feeder across one day. So you can see peaks in demand. There's an effect which I learned last night, it's called the Coronation Street effect. So at about 7:45 PM, which I guess is somewhere here, you see a spike in demand. So when there's a commercial break in Coronation Street, the whole of the UK gets up, puts the kettle on, makes a cup of tea. You see a spike in demand. It's quite regular, it is predictable. There's other aspects which are less predictable, so things like just general patterns of life, they change by the day, by the season, by the location. You've got a spike at 6 AM when people have a shower, and then a spike at 7 AM when people have a shower later on. So it goes up and down. This is one feeder which might supply 50 to 100 homes. Now, what we're looking to do is to understand really where people are using electric vehicles. Because if we understand that, we can plan where and how we need to upgrade the network. Because the last thing you want is people to run out of power. People expect electricity just to work. You plug in something, it just turns on. The level of acceptability for power outages is very, very low. So if we can look at this data and work out where people are using vehicles, then we can use that to plan out and to map out the upgrades required. If we looked at the data per house, that would be very easy because it's a big change. But doing that's very expensive. So if you can do it at the substation, it's a lot cheaper, a lot more effective. If we were to superimpose onto here, say 3 rapid chargers, so these are like the meaty 3-phase chargers, you can see the amount of load required is quite big. And you have to plan the network capacity based around the peak usage, not the average. So if your power demand peaks 80 kilowatts, you have to build a network that can handle that. And that's expensive. If you can move that demand so it happens across a longer period of time, you lower the peak demand and you can save money. And the forecast suggests that by 2030, 2050, if we've all bought electric vehicles, we're going to need major upgrades to the power network, costing around £2 billion and causing major upheaval in terms of roadwork, etc. It's a real nightmare. So be interested in looking at ways to manage demand, to shift the peak, and potentially make a better use of the network. So this is the project. It's called Electric Nation. And it's a collaboration between Western Power, as well as EA, Drive Electric, Lucy, and TRL. So these are the big players in the industry, people who produce power, who sell vehicles, who sell charge points, people who sell the equipment in substations. And they're interested in understanding how their industry is going to change. It's a trial that lasted for 3 years, and the idea here is to understand smart charging. If we were to say to consumers, we want you to be flexible in the way you charge your vehicle, how can we do that? How can we do it so it's fair, so it's reliable, so there's no surprises? Like if you come home, you plug your vehicle into charge, you expect it to charge up. But if it's not charged up, and then you come to use your vehicle, you want to go to shops, that's not a good situation. So this is all about understanding what kind of impacts adaptive charging would have on customers. Are they going to be in favour of it, or are they going to be, is this going to be like the new poll tax? How would it work, and how can we incorporate customers' preferences into their behaviours? So what we did was to do the modelling here. So we did a lot of software work to build models, to interpret the data from substations, and see if we can pick out when and where people are using electric vehicles. So how often, how do they charge them, what are the patterns, and also understanding how much background load can there be, how much noise can there be before we can't see the signal that we need. Okay, so I'll move into a bit about talking about the process we follow. And this is probably a fairly traditional process, getting some data, processing it, sorting it, building a model, and then looking at deploying that to somewhere. But also a key part of that is sustaining the model, so looking at the performance of it over time, checking that it's still doing the same thing that it did on day 1, it was on day 10 or day 100, incorporating new data, remodeling. So that's all part of sustainment. And I guess in a bit more detail, data collection is often like the biggest part of the project for us. Choosing a model, fine, developing it, yes. But actually, until you've got your data in the right format, in the right kind of structure, in a format that you can use to learn from, then you can't do anything. And I'll talk here a little bit about augmentation and data generation. So, in most projects, you're constrained by the data. It's very rare that you've got too much data, or it's too easy to process. So, data augmentation, very powerful. And I'll talk a little bit about class imbalance, as well as the models we used and why they were used. Okay, so for this to work, we actually had to go out and collect data. There wasn't any data existing on the vehicles, so we got a bunch of vehicles, we plugged them in, and we recorded their power draw. So how much power they're using, and various things like real and reactive power and harmonics, which I'm not going to go into today, but a key kind of load characteristics you can monitor as well. If you're interested, this is how the charge signatures look. So we did a bunch of different vehicles, and they were charged for different lengths of time. So you plug it in, you turn it on, and you record the power draw. What you'll see is that at the start, there's pretty much a jump. There's a step change as they're turned on. Whereas the characteristics, as they reach full charge, vary between vehicle and charge type. So some tail off, some use switch mode to carry on charging for a bit longer. In these graphs, the blue is the real power, and the orange is the reactive power. So that's the components that's out of phase. And in a bit more detail, so that's a plot enlarged for a Nissan Leaf. So here it's turning on, here it's turning off. And the key part is the middle of it is variable length. So we don't know how long they're going to charge it for. It could be for 5 minutes, it could be for 2 hours. So we look for the start and the end events rather than the middle bit. And we did a bunch of labeling. So here we've got 3 classes: null, nothing happening; 1 is turning on, 2 is turning off. So now we're starting to get to the position where we've got a data set where we can learn from, because we've got raw data and we've got labels. Now, unfortunately, we've only got about 10 traces recorded per vehicle type, about 200 different signatures. Go on.
Last question now.
Go on, why not?
Okay, so why is the charging phase also labeled as 0, not something else? That was surprising to me.
So why does the
thing in the middle, why is it also labeled as 0?
Oh, that's a good point, actually, yeah. So the question here is why is this section in the middle, the variable length section, labeled as 0? It's a good question, and technically, actually, you're right, it should be 3. Because of the way, because we're superimposing signal onto background noise, actually, you can only detect changes. So when there's a consistent signal, you have no way of knowing if that load is from a vehicle or from a different source. So perhaps my next slide will show some more depth. It's essentially, we're looking here for changes. So in the middle, because it's so flat, there's no change and you just can't see it. Okay, so what we had to do here was actually to generate data, because we had about 22 vehicle types times about 10 recordings a beat, about 200 recordings, but that's not really enough for the training we wanted to do. So here we've taken a load of background data. So the blue line is the power draw when there's no electric vehicle, and we've superimposed the green line, which is the data we recorded ourselves, on top of that. So that gives us a test sample here, where we've got normal background power load and also superimposed onto it a vehicle charge signature. So we know when the start, when the end is, and we can use that to train. So this works because the assumption of superposition holds here. You can add the two signals together, and that's valid. You can't do that in all cases. So for example, if you're working with pictures and images, you can superimpose one image onto another one, but you don't account for things like shadows or reflections or the edge cases or the edges of the image. So you can't use this technique everywhere, but if you can superimpose and augment your data, you can make your data set to be pretty much as big as you want it to be. You can generate data that's semi-synthetic, and as long as your assumptions about superposition hold, you're probably okay. To get the data into the network, however, we need to get into a nice structured format. So we move a sliding window across the dataset and break it into 30-minute chunks. So what we actually add here, the data is really quite low res. We're recording power data at 1 minute intervals. So in 30 samples is 30 minutes. And that's because getting the data out of the substation actually is quite hard. They have quite limited backhaul capacity, so you can't be funneling data real time off the grid. You have to record a day's data and then send it over a 2G modem. It's quite a long story. Essentially, the capacity to transfer data is quite limited here. So we're working with very low res data. And what we've done here is we've normalized it, so we've scaled it down. So whereas your power draw is between 0, maybe 100 kilowatts, we've transformed that and scaled it down between -1 and 1. So this kind of feature normalization, it's not something you have to do, but by doing it often you can train a lot faster. And also you're normalizing your features so they're the same kind of scale. So that's an important step in preparing the data. Finally, a note on labeling. So we label each 30-minute period with one label which says, is there an on event, an off event, or nothing? That's quite a simplistic way of doing it. And it has limitations. So the limitation here is that you can only really account for a single event in one window. If you have multiple cars turning on, you can't see it because you have one label that tells you what's going on. So a more advanced technique would be to label each time point individually, and that way you can detect multiple events. That's not something we've done here. That would be a next step. Okay, so I'm going to talk a little bit about class imbalance and bias. Really because the data set here is very imbalanced. And this is quite an example of what it's common in virtually all kind of real-world machine learning, is that the data set is always biased. And that can lead to a bias in your predictions. So here, for example, if you're looking to predict the colour of a fish, you'd get a pretty good result just by predicting blue. There's only one red fish. So actually, if you always said the fish is blue, you'd get to like 99% accuracy already. Now, that's very good for the blue fish, but actually that's heavily biased against the red fish. Okay, if it's fish, maybe not important, but if you're dealing with, with gender or race, that's more important. Now, in our data set here, we have lots of time when nothing's happening, and then a few cases where there's an event, where it turns on or turns off. But it's heavily balanced away from the events. There's a lot more nothings than there are events. Now, if you just take the data as it is, so train on that, and then you use that in your validation, that will generally give you the highest performance, but also the most bias, because your network learns how to predict bluefish really well, but it only sees a single example of a redfish, so actually its capacity to understand what is a redfish is very limited. If, on the other hand, you rebalance your training set, so you have equal numbers of each type, this will give you the lowest bias, because the network learns equally about each class. But it does give you lower performance, because you spend less time learning about the bluefish, which constitute most of your data set. Unfortunately, there's no easy answers here. It's about trading off performance against bias, because there's not a solution that optimizes both performance and bias. So here's our data, and the graph on the left shows the data before we balanced it. So you can see it's 95% nothings. What we did was relatively simple, which is just to downsample the majority class, so to remove some of the nothings, if you like. That increases the proportion of the on and the off events, but we leave the data set a little bit skewed. And there's a reason for that, which I'll go into a little bit. Okay, so here's the network. We're using convolutional layers as the feature extraction. So convolutional layers are looking at the mathematical convolution between what's called a kernel and between the input. And it's like a pattern matching. So when the two are similar, you produce a strong result. We have stacks of these. So the first one looks at patterns in the input. The next one looks at patterns in the patterns of the input. The next one looks at patterns in the patterns in the patterns of the input, and so on. I won't go on. And then at the end we have dense layers, which are the classifier. This is what takes the patterns we found and outputs a classification. Okay, it's using supervised learning. So in this we show the network what the true answer is. So here the weightings on the nodes in the output represent probabilities. And during training, we're certain that this sample is an on event, an off event, or nothing. So we apply that weighting onto the output. When we come to evaluate new data to predict, then the network calculates prediction, and the value of the output is its confidence in that the input data belongs to that class. Okay, some performance results. So this is a confusion matrix. Everyone know what that is, or seen it before? A few. Okay. So this is a way of reviewing the results of a classifier, and it shows how the prediction relates to the true value. So we have our three classes along the bottom, along the side, and ideally we want to see all the values along the diagonal going forward. And here it's like the darker blue. That's because when the true event is a null, it predicts null. When the truth is an on event, it predicts on, and etc. You can see it's not perfect. So we want the data to be here. Oh, sorry, I lost it. So along the axis, down the middle. This area at the top represents false positives. So that's when nothing's happening, but the network predicts something is happening. And the bottom here represents false negatives. So that's when there is an event, but we can't see it. Now, for this application, it's a lot better to miss an event than to falsely predict an event. And that's a little bit down to the business case. So you'd rather not put upgrades in a place where they're not needed, rather than do that, because that's expensive. And actually, you will probably detect if you need upgrades with a different technique. So you would prefer some bias. And that's why we left the training data set to be slightly biased, because actually we prefer that we get false negatives rather than false positives. If you were to balance the data set very evenly, then you'd see roughly even numbers of failures here as you are down here. And one thing that we see also is that it's a lot easier to detect the turning on than the turning off. And if you remember the traces, go on.
Is there a business reason why you need to distinguish between on and off? Because off, by definition, goes to null.
Yes, so the question was, is there a business reason why we wanted to distinguish between ons and offs? And in answer, maybe. So you definitely want to find the ons, because that's a vehicle being used. You wouldn't mind knowing how long they're charged for, whether they're being charged every day for an hour, or like every other day for 2 hours. But there's a complication with the offs in that it's very hard to pair up ons and offs. If you have multiple vehicles on one street, you don't know if that off is from the car at the first house or the second house. And secondly, if you remember from the graphs, the on's a very sharp step change, where the off is a curve. So the rate of change is much slower, and so it's sort of hard to detect. So it would be nice to know the offs, but it's not really crucial. Does that answer it?
Yeah. Well, then you probably get
Yes, yeah. And if you're trying to detect a vehicle, if you were to miss the on, but you detect the off, that's still some data you can use. So there's advantage in knowing it, but actually with an accuracy of 74%, it's probably not really usable for most things. Okay, so I thought I'd put an example of where we went wrong. This is in model development. So when you're looking for a signal with noise, when the noise is very low, it should be very easy to find the signal. That's kind of obvious, yeah? It's like looking for a needle in a haystack. If the needle is very big, it's easy to see. So this is a graph of how the detection probability relates to the background load. And so when there's more background load, more things happening on the network, it's harder to see what you're looking for. So that can make sense that actually the performance drops off as you increase the background load. That's what you would think would happen. This is confusing though, because as it gets lower, you would expect to see the performance to be really good. It's actually very easy to see a vehicle being charged when the background load is 10 kilowatts, because the vehicle draws 7 kilowatts, so it's super easy. This is the data distribution we used in the training, and as you can see, there's no samples down at 10 or 20. So actually, we've built a system that can't see very low powers. It's just, there isn't a training example that represents the case we're using. So this is an example of trying to infer a sample that's outside of the training set. It's different. Now, the reason that was chosen was because that's a relatively realistic set of data. So actually the use case of having a feeder with a background power of 10 kilowatts, that's quite unusual. But still an example of where the model has fallen down. So I thought that was interesting to show. Okay, so just a little bit on deployment training. So once you've got a data set, you're getting data every day, there's new data, you'll be training, so hence you're going to get a model, and actually quite a few as you develop it. We've heard at this conference about both methods of deploying it. One of them was Flask, I went to yesterday. I heard about Unicorn as another way to serve models. Now, this works on TensorFlow, and the TensorFlow offering is called TensorFlow Serving, surprisingly. we like TensorFlow because it's an open source framework that you can build models in Python and then you can deploy it onto mobile or inside a C++ framework. So it's very versatile. And TF serving is one way to serve models to the web. And the way I would do it is to use the Docker image. So you can just kind of download the Docker container, and that's a pretty much pre-configured TF serving. And if you need to scale that, you can use a container orchestration tool like Swarm or Kubernetes. These let you manage like a set of containers. So you can say, I want to keep up 1 running or 10 running or certain capacity running. So these are tools to make the job easier. And the Docker image of TF serving, you can be up and running in kind of half an hour probably. And if your use case requires running it at scale, you can then have many containers. So you don't need to have like one big server, you can have lots of little containers running across a cluster. And that model is very easy to port to something like Google Cloud or AWS or Microsoft Azure. So that's a very versatile form. And it's not the only way to do it. You can use Flask, you can use some of the low-level APIs, but that's the one that's supported by TensorFlow, so it's quite a neat way to do it. Okay, going to wrap up with just a chat about future smart grid. So we looked at active demand management, and this kind of falls under the nickname of V1G, if you like. This is like the grid is controlling the demand, and you can use that to move the peak to a later time. And that's kind of applicable to electric vehicles because they're charging up. So actually there's a bit of flexibility in when the demand needs to happen. It's not a kettle or TV. You can't cope with your TV being shifted back an hour, but you can with your car. What we're seeing as well is kind of like a shift in the way that we use energy. So traditionally, you've got this big peak in the evening, and the way you might supply that is with a power plant called a peaker. They're often gas-fired because they can start up and stop very easily. And so with a gas-fired peaker plant, they might only run for a couple of hours a day. So the power that they supply is very expensive. And that's generally like a trend in the industry. So if you can supply power for short bursts, but with a rapid response time, your output is worth a lot more. Whereas if you're like a big coal-fired power plant that must run all day, every day, then the cost or the value of your electricity is lower. So rather than supplying this big peak in the evening using things like gas-fired power plants, the use of energy storage is becoming more viable as the cost of batteries drop, and that's driven by the growing demand, particularly from electric vehicles. And this idea of energy, AI-led energy arbitrage, traditionally these peaks in demand have been managed by schedule. So we know that in the evening at 6 PM we need more power. If there's a sudden surge in demand, then there'll be a power controller on the phone to a hydro dam asking for more power. Whereas that's shifting. Now that we've got a varied mix of power supply, we've got local generation as well as storage. That's we're seeing the shift here towards a software-led architecture where there's a control system that requests power from local storage or from other sources of power, other generation. And that's a change that will be happening probably for the next 10 or so years. The last one, which I think is quite a big thing, is vehicle to grid. So we have this growing fleet of vehicles, and each one contains a battery. The battery capacity is growing. It's actually a vast storage pool of energy, if you like. And the idea of vehicle to grid is that the power flow between the grid and the vehicle is two-way. So you can both charge the vehicle as well as charge the grid. Now, that's quite a complex arrangement because you need to be pumping back high voltage power into the grid. However, it's an opportunity really because the amount of capacity once we start buying vehicles in bulk will be absolutely huge. So this idea of having to fire a power plant just to supply the evening demand, that almost goes away. You have a much more uniform demand, which means you can plan the demand better. So this is a technology which actually is being trialled at the moment, and I imagine will be very big in the near future. Okay, that's all from me. Thank you very much for your attention. The slides are all available online, and do feel free to connect or get in touch if you have any questions. So, thank you very much.